Well, good morning, everybody. Thank you for attending this morning's class. My name is George Carey, and I work for FIA, and we are presenting this morning, as it says on the screen here, hydronic system components, or trying to understand all the various components that make up a hydronic system, specifically around the boiler and the boiler room. And that's our plan for our presentation this morning. I'm going to end up muting everybody just to try to minimize background noise as we go through this presentation. But there's a chat feature that's at the bottom of your screen where you can ask a question. You can kind of text a question. And I have Rob Ellis, also from FIA, who'll be kind of monitoring that. And then obviously at the very end of the presentation, I'll unmute everybody. And if there's any residual questions that need to be answered, we'll do our best to see if we can, answer a question. So without further ado, we're going to kind of jump into this and see how it goes. So let's see. So this is just a quick little picture of a residential home. It's from one of Bell & Gossett's kind of wholesaler product guides. And I thought it was kind of a neat little thing in that it kind of listed out a lot of different components within that hydronic system that Bell & Gossett, in our world, we're the Bell & Gossett reps, but that touch. And whether it be a boiler, whether it be air separators, expansion tanks, circulators, obviously, perhaps heat exchangers, trying to show a little pool heating, trying to show some snow melt in the driveway, a little radiant heat, as well as some more maybe traditional heating baseboard. So the point of it all is, it does a pretty good job of, kind of touching what we're going to talk about. And I thought B&G did a pretty good job. And then I was doing some research, and I found this picture, and it's out of a like a 1945, 1948 catalog from Bell & Gossett. And I'm like, son of a gun, it's the exact same thing, what they were doing back then. Just showing a picture of a boiler, which obviously Bell & Gossett's not a boiler manufacturer, but they handle all the other components that make that system work, whether it be expansion tanks, monoflow fittings, relief valves, circulators, pressure reducing valves, flow control valves, all the various components, air control. So what they were doing then, we're trying to do again, X number of 60, 70 years later, which is kind of amazing to say, but this is where we're at. So the concept of this morning's presentation is just to kind of break down some of these various components and what do they do? What don't they do? What happens when they don't do what they're supposed to do? And so either helping you on a design standpoint or perhaps an installation. And sometimes just as importantly, if you're out troubleshooting, if you're out in the field and you got a problem in a heating system, if you understand what it's supposed to do, it makes it easier to perhaps figure out when it's not doing what it's supposed to do. So that's the idea. I write for a couple different magazines. Some of them go across the country. And so I have a lot of correspondence with different, contractors, oil technicians, et cetera. And I get a lot of email back and forth, troubleshooting this, that, and the other thing, steam and hydronic systems. So every now and then they send me various pictures of problem jobs that they were on. And so a gentleman had sent me this, and I thought, wow, that's probably a pretty standard, unfortunately, standard basement, in an apartment building or in a home. All the pumps are on the return. Not sure all of the people that are attending this morning that might have attended our fundamentals of proper pump location yesterday. But as you can see, all of the pumps, it was a pretty standard practice in the industry, especially residentially, to put the pumps on the return, which, as we spoke about yesterday, that's really not ideally the best location. I found this in an apartment complex in Boston, Massachusetts, a little while ago, a few years ago, and I was out with a contractor. And I was mesmerized by this picture. I can't understand why the boilers are at almost like a V shape. I don't know what their thought was or what forced them to do that. It looks like they got a pump convention. I think almost every pump manufacturer is represented. Real level and plumb, nice and neat, just like, like you'd want to see. And the amazing thing is probably upstairs, the people get heat when the thermostats call, which is just amazing. And it kind of speaks to the point that hydronic systems can be relatively forgiving. And then when you bump up against that problem job, not you, but whatever's gone wrong has really gone wrong, because you know, even looking at something like this, and it's still, they had heat upstairs. It's kind of crazy. Someone sent me this picture. This is kind of amazing. And what it is it's a bank of, I don't know if you could see that word there, but it's a bank of hydrotherm, which was very popular for a period of time, probably in the middle to late 70s and into the early 80s. They campused the engineering community and got a lot of jobs. But what I was looking at is this. You look at all of these zone valves. I didn't bother to count them, but there's got to be close to 20. And if you look at the size of the piping that's supporting all of these zones, it's way undersized relative to what potentially if all of the zones were calling. And then off to the side here, you see the old famous Everhot sidearm heaters for domestic hot water, which would mean that these boilers stayed hot 24/7, 365 to be able to support any kind of domestic call, because it was instantaneous. So not on your high efficiency standards, so to speak. But anyways, again, it's just some of the stuff you see out in the field. It's amazing. This always caught my attention. This, you got this little boiler here. You got this little Grundfos pump feeding this manifold of like 15 or 18 zone valves, looks like maybe Honeywell zone valves, feeding PEX tubing. And this certainly screams of a picture of do-it-yourselfer. It's amazing. And again, how they get heat upstairs, it's just amazing. Got a little expansion tank hanging off to the side here. I don't see any air separation, so I don't know how they're handling the air that might be developed as you heat the water, you know, in the boiler plant. So as we jump into this, first component I was going to talk about or talk with you is circulators. They're kind of the heart, so to speak, in terms of at least moving whatever heat we generate in the boiler out to where the people live. So someone sent me this picture, kind of looks like it needs a little TLC, so to speak. They get the cobwebs, we get wires hanging all over the place. But a collection of probably older three-piece, looks like either Armstrong or most likely, I see some labels right here, probably B&G pumps. And it looks like as these pumps possibly fail and they fall onto the floor, get laid on the floor, they might have been replaced by some of the smaller style cartridge pumps that have, you know, taken over the industry over the years. But it's just, you know, it's just amazing with some of the stuff you bump up against when you walk into a mechanical room. So first style pump I want to talk about is just a cartridge style. You see them, there's kind of two versions here. And one of them is referred to as a permanently lubricated. So it's using oil that it's constantly being reused. And then the other over here is a water lubricated cartridge style pump. And they've been very popular probably for the last 30 years or so, maybe even more, 40 years. But typically in a residential application, sometimes you might see them in a light commercial, but typically residential, but small, self-contained, you know, flanged, you know, pretty straightforward stuff. As you get into some of the larger size pumps, meaning probably larger capacities, larger flow rates, greater pressure differentials, you can have the inline family of pumps. And then sometimes in these inline pumps, you can have what they refer to as a three-piece pump. And the three pieces being the volute, the wet end of the pump, the bearing assembly, which is the connection between the motor and the impeller, and you'll have a coupler that kind of connects the shaft of the motor with the shaft of the bearing. Was kind of a workhorse for the hydronics industry at the beginning when things were being transitioned, when systems were being transitioned from gravity hot water to forced circulation. And I'm asking a question and I know I can't hear the answer, but if you've ever heard the expression a booster pump, that actually came from Bell and Gossett, and it was kind of used as a marketing image, if you will. And the thought behind it was, instead of relying on gravity circulation, by installing this booster pump, we could boost the heat around the home faster than simply relying on gravity. And it kind of stuck over the years throughout the industry. Over here to the right, same inline, but now it's what we refer to as a vertical inline. No bearing assembly. The motor assembly just sits right on top of the impeller that's sitting inside this volute here. A quick comment, I had mentioned it yesterday, so I apologize to those that were here yesterday. But when you're out in the field and you're you're out there maybe troubleshooting, you're trying to figure out what's going on, most manufacturers will have castings, they'll have arrows that you sometimes see, and it's indicating the direction of flow. How's the water moving? What direction? Up or down, left or right? But a lot of times, the mechanical room might not be lit up or as accessible as you'd like. And so just a quick little note, if I can share it with you, is if you can't find that arrow, but you can see this hump right here, this bump on the volute, the wet end of the circulator, that's an indicator that the flow is moving down through into this hump or bump and into the eye of the impeller. Same thing over here. It's moving in this direction into the eye of the impeller, being discharged out the discharge port. ECM circulators, they're starting to take over North America, certainly over here in Hydronics Alley in the Northeast. It's becoming a very popular technology, and the utilities up and down the East Coast here are playing a big role in it. They see the value in the reduction in energy consumption, kW consumption, by moving to this technology. So it's still a circulator, still has an impeller, still has a motor. How they do what they do, though, is different in terms of having a drive, and inside here there's a printed circuit board, like a microprocessor. So all of these style pumps have some form of intelligence on board. Just real quickly, ECM, it stands for electronically commutated magnetic motor. So what happens is there's a permanent magnet on the rotor, and it eliminates need for input power to magnetize the rotor. So the magnets are already sitting there on the rotor. Motor is microprocessor controlled to keep the stator current in phase. And then lastly, power is pulsed on and off electronically to create that magnetic field. And the process is known as commutation, hence electronically commutated magnetic motor. Real quickly, picture speaks 1,000 words. The magnets are on the rotor, and that pulsing electronically on and off to create that magnetic field, and the magnet reacts to it. The faster you pulse it, the faster the rotor turns, or what's attached to the rotor, the impeller, so the RPMs, the speed, the GPM that the pump can develop. And just as importantly, and more from an economical standpoint, the slower you rotate it as system conditions change, the slower it rotates, the less kW it consumes. We'll be putting on a full-blown Zoom. I don't think it's next week. I think it's the following week, so keep an eye out for it. But we're going to get into just the whole why and all of the applications and possibilities that you can go with an ECM circulator. But I just want to point it out that that's another becoming very popular in the residential and light commercial space. As you move into the more of the commercial with bigger loads, greater flow rates, et cetera, you get into what's referred to as base-mounted end suction pumps. And the end suction means on the end, at the end of the pump, that's where the suction is. That's where the return water, or from the maybe the boiler, if you will, is entering into the impeller that's spinning in this casing here, and then it's going to be discharged out the top. So end suction, discharge out the top. Close coupled with the little foot right here, or again, a bigger, almost like you could say a three-piece. You got your motor sitting here on the motor brackets. You've got your coupler that's connecting the motor shaft to the bearing assembly, and the impellers on inside the wet end of the volute. It's very popular, very common in commercial applications. You'll see it a lot. Can handle a pretty good capacity. And then another style pump that's even bigger, that's kind of the workhorse, if you will, is referred to as split case pumps, split case base mounted. And they can be, vertical discharge, vertical return. They could be, you have different configurations, as you can see here. But this is definitely known as the kind of the workhorse. When you're dealing with thousands of gallons a minute, and that's not uncommon in hospitals and college campuses, in large facilities, we need a lot of GPM. Either chilled water is a big application, but it can be as well. The thing that I just want to reference, the split case. What's referring to the split here is this dimension right here. It's almost like a V shape. And what's happening is there's an impeller sitting inside here, but the water doesn't enter just in one side. Like here in an end suction, the water enters, hits the impeller's spinning. We've got some load back here, some thrust on the bearings, but then it handles it and it discharges out. On a split case, what happens is the water comes in and it splits equally. And I have a quick drawing here. And the impeller is referred to as a double suction impeller. So I have water that comes into that casing right here, and then it splits equally. The idea is to be equally, if it's installed properly, to load that impeller equally, and it removes a lot of that thrust. So if I had thousands of gallons a minute coming at this impeller right here, there's a tremendous amount of bearing load that takes place in it. That's what will kill, that will shorten the life of and require a lot of service work. These split case pumps, which are much more expensive, but also perfect for these high capacity applications. So I just want to kind of make you aware of all the different pumps that you might bump up against. Sometimes the question gets asked, either from the contracting community or even the engineering community. And they'll say, when do you select? Where's the cutoff point? And it can vary, but as a general rule of thumb, it's kind of common throughout the industry that say, when you're over 1,000 gallons a minute or so, you might want to move from your Ford F-150 and buy your Ford F-350. And that was an analogy that was presented to me that made a lot of sense. You could do it with this, but it's going to get beat up pretty quick. This guy, that's what he's built for, to handle those 5s and 10,000 gallon a minute applications. That's the pump. So again, centrifugal pumps, we talked a little bit about it yesterday. So for those that were here, I apologize for repeating. For those that are new, we just want to share with you briefly, what's really going on inside there. And it's called a centrifugal pump because it's a mechanical device designed to move fluid by means of the transfer of rotational energy. So centrifugal, rotational energy from a driven rotor, in this case, an impeller. The fluid enters the rapidly rotating impeller along its axis, and that's the eye, and is cast out as that's spinning, that rotating, that centrifugal force, adding velocity along the circumference through the impeller's vane tips. What does that mean? Here's a kind of a line drawing of an impeller, face on, and then a side view over here. So we have this eye, and that's where the water enters into. And then as the impeller is rotating by the action of the motor spinning, the water is thrown along these veins, and as it rotates from the eye to the outer edges, the velocity just gets faster and faster. And so we have this velocity that's being added to this water. Is a better picture, more probably of a end suction pump. And as it's spinning and this velocity is added, when it discharges out the volute right here, the discharge port, it's this velocity is converted, if you will, to pressure. And in a closed loop system, really what we're referring to is pressure differential. So I have a certain suction pressure, and then I have a discharge pressure. And for the water to move in the proper direction, I always have to have a lower inlet pressure and a higher discharge pressure, because high pressure goes to low. And that's just kind of a fact of Mother Nature. And Mother Nature hates an imbalance, so she's always going to try to cancel that out. And the job of the motor is to keep this pump spinning, taking this water, throwing it out away from itself, adding this velocity. The velocity gets converted to pressure differential. Now all of a sudden I have a high pressure on the discharge, a low on the suction. There's my motive force to circulate, to move this water throughout the system. And so that's what's happening. That's what a circulator does. It's a centrifugal pump, adds velocity, spins it off the vanes of the impeller. There's all kinds of designs and different diameters, thickness. If you're doing 1800 RPMs versus 3400 RPMs versus 11 or 1200, there's all different. That's all from the manufacturer. That's all engineering. That they get involved with the pump manufacturers. That's their deal. That's how they, build the pumps based on certain applications, et cetera. But the general concept is it's a centrifugal pump. Water enters the eye, gets flung along the veins, and discharged out the top. The point of this picture here is to just try to remove any misnomer or whatever theory, a thought, I should say, not theory. The job of the circulator, like we just talked about, is to move the water throughout the hydronic system, be it chilled water, hot water, both, whatever the case may be. Over the years, I've had conversations where someone will call me, and somehow within the conversation, it'll become, hey, I think I need a high-headed pump. Like, okay, well, why? He goes, well, I'm in downtown Boston, and I've got this 5-story, brownstone, and I got to get the water from the basement all the way up to the high point, and up to the highest piece of baseboard in a cast iron radiator in the top floor. The circulator's job in a closed loop system has nothing to do with that. It has everything to do with overcoming the frictional resistance that's offered by the wall of the pipe within that system. Same as, and that's why we show this picture of this Ferris wheel. The motor on the Ferris wheel's job isn't to lift these chains, because whatever energy is required here, an equal amount is gained falling down. Same thing. If you look at it as whatever energy to go up that riser, I'm gaining it on the riser coming back down. But what I do have to overcome, and that's the job of the pump, and this is the job of the motor, is the frictional resistance to get this thing going, to get it spinning. So pump head has nothing to do with height of the thing, it has everything to do with frictional resistance. Quick drawing here is just showing an expansion tank, a pump, and say it's on a horizontal plane, there's no vertical height, and it's filled to 12 pounds. So there's 12 pounds everywhere. Turn the pump on, and it discharges, and it develops, I should say, 20 PSI perhaps in this case. So that 20 feet is reflected at the discharge. So that's my highest point of pressure. So I'm registered on the gauge 12 plus 20, 32. My lowest is my 12 on the suction. So there's my motor force to move this water throughout this system. Now, obviously, that differential that I developed at the pump is reduced as it moves throughout the system. The reason being that frictional energy is eating up that pump head that the pump developed as the water moves throughout that whole circuit. Looking at pump curves real quickly, this is just a quick example, but pump curves basically are almost like either blueprints or the DNA of what a particular pump can do. This is just a selection of some Series 60 B&G pumps, different model numbers, and each model number represents various capacities. When you look at a pump curve down here on the horizontal, you're looking at GPM, and on the vertical left-hand side, it's in feet of head, total feet. What kind of frictional resistance can this pump develop to overcome and move a certain GPM that I need down here? Real quick, sometimes you can use a pressure gauge to confirm what is the pump moving, what's the GPM. And the way you do that is you'd have a gauge on the suction of the pump and a gauge on the discharge, and you want to read that differential. So I have, as an example here real quickly, I have a Bell & Gossett 1510 2AC, and I'm out in the field, and this pump has a range of a 7-inch wheel all the way down to 5 inches. And maybe I don't have a tag, or I don't know what the diameter is. So I want to first, before I try to figure out what it's doing, I want to know what size wheel is inside that base mounted pump. So what I can do is I have the pump off, and both gauges are reading 20 PSI in this quick example. To confirm the diameter, close the discharge valve. Now, you're only going to close it for a very, very short period of time, because you never want to have a pump run dead-headed because of the energy it can develop in that water that's going to be sitting inside that volute right there. But you do it just very quickly. So close it, turn the pump on, read the differential. What's my suction? What's my discharge? So 20, 35. So I got a differential of 15 PSI. The next step is I want to apply that information to this pump curve. And when I look at 15 PSI, I realize I convert it to feet of head. I got about a 35, 36 feet. I can confirm that, in fact, someone had trimmed that impeller to 6 inches. So then the next step is say, okay, now to establish what's the flow rate, open the discharge valve, obviously, turn the pump on. If you have a bunch of zones, you got to make sure all the zones are open because you want to know the total flow rate, what's it capable of. And when I do that and I turn it on, I read suction of 20 and I read a discharge of 32. Now, of course, it's going to be less than when it's deadheaded because now I have some flow going on. So I have some flow rate taking place. And I want to figure out, okay, what is it? So again, read 12 PSI, go back to my pump curve. Where's 12? And I say, okay, there's 12 PSI. What do I do? What you do is you read horizontally until you intersect that particular pump's impeller curve or pump curve. So in this case here, I've confirmed that that pump's pumping about 120 gallons a minute. That's a way of using gauges to determine flow rate. Of course, when you get into some of the newer technology, a little smaller capacity perhaps, but some of the ECM pumps, they actually display it for us. They give us that information right on the cover, right on the drive itself. So that's pretty convenient. Real quickly, circulator location. Again, we talked a little bit about this, or actually quite a bit about it yesterday. Quick answer, yes, it does. It's very important where you locate the circulator if you don't want to have a system with problems. Or if you mislocate it or you bump up against a system that does have it in the wrong location, it could be the source of why you're there, perhaps troubleshooting. Real quick, pump away from the expansion tank. All of his differential will be positively added to the entire hydronic system, which is a good thing. Conversely, if you pump towards an expansion tank, the point of no pressure change, all of the pump's differential is negative, it's dropped. So from the pump world, I still have high here and I have low here, so I have circulation. The problem is I've lowered the system pressure, it's fill pressure, it's static pressure, and I can get into the point where I create vacuum and I can pull air in and it can create all kinds of problems. So we always want to pump away from the expansion tank. These couple of drawings are older, so they're showing an old steel. The exact same principles apply to diaphragm and bladder tanks. And real quickly, this is a 2-second dissertation. The reason that exists, that whole principle exists, has to do with this. Water is not compressible. So the only way I can change, air is a gas, and a gas is compressible. The only way I can change the volume of air, which would mean change the pressure of the air, is by changing the volume of water in this system, this hydronic system. By simply turning on a circulator, do I change the volume of water in that system, or do I just simply circulate it? And the answer is no, I do not change the volume of water. So if I don't change the volume of this water, I don't change the volume of this gas, this air, which means I don't change the pressure. So this has become known as the point of no pressure change in the hydronic systems. And we always want to reference it and have our pumps pump away from that point. Moving on, next component that we bump up against, flow control valves. So why were they developed? Why was a flow control valve, a flow check is also another term that you hear out in the industry. Why were they developed? Well, it started back as they were converting from gravity hot water and moving to forced circulation, because with gravity, they'd never be able to open that check. But what they also started combining with the heating, using this boiler for heat for the house, they would have domestic hot water located off the boiler. So the boiler would stay hot all the time. Well, they quickly realized that if they didn't have some type of weighted check here to prevent the water from circulating, even in the summertime, I get this hot water, which I need the boiler to be hot to provide the domestic hot water. I would have heat would migrate, maybe not as fast as if it was gravity hot water because the piping might be smaller, but I would still have heat would migrate. Heat would go to cold. And so they quickly realized, okay, this is why this thing showed up. I don't want heat leaving this boiler unless that circulator over here turns on. Once he turns on and he creates that differential, it'll lift that weighted check out to the system. So a couple of pictures of some residential swing, they call these guys sweat checks, or they could be NPT, threaded SAs, they refer to these guys. So you could have a straight angle on 3/4 inch to 2 inch, where you'd either come up and go off to the left and you'd plug the right-hand port, or you'd go straight through right to left and plug the bottom. As you get into some of the bigger ones, you had to actually choose, is it an angle or is it a straight through? But all of them had the same purpose: prevent gravity circulation from taking place until that particular zone pump came on. Now release it, open up. Recently, and I say recently, in the last probably 10, 12 years, spring checks started showing up on the market. And so this is just another version of a spring check. Some of the advantages of the spring check was, with these guys, they have to be level and plumb to make sure that that stem, that weighted check that's sitting inside here, is seated properly, straight up and down, so that it does its job. A spring isn't quite as concerned with that because I have that spring tension, so it keeps it closed. So it had a little more flexibility perhaps in some of its installations. This would just be a quick snapshot of an installation manual of some of those, either sweat check or the more traditional NPT flow control valves. Commercially, a flow control valve, you might see it in one of these base mounted pumps, and it's referred to as a triple duty valve. And as the name implies, it has three functions, triple action. So what it can do is it can act as a balance valve. It can act as a soft seated check, which is, there's my flow check, my check valve. And then it also can act as a service valve. It can be a positive shutoff. So from a balancing standpoint, they have this stem here that you would crank down, if you will. They have some numbers here which indicate a pressure differential. It has a soft-seated check inside, so that is my spring check, and when that pump turns on, it opens that check and discharges the water. And then if I had to service the valve, if I had to service the pump, I could rotate that head all the way down, and it would act on the discharge side of that pump as a service valve. I still have to isolate on the suction side, but anyways, it was a triple duty valve, very popular. It's around, over the years, one of its popular applications that actually, as energy codes are starting to change, might lose some of its flavor, had to do with when a pump got spec'd, so the design conditions were originally established. Sometimes there'd be what you could refer to as a CYA, cover your tail. So they'd maybe put a little more head energy, a little higher head than was necessary. And so when day of commissioning, when the pump was actually turned on, you want to find out exactly what it's doing, and you realize that it's over pumping because the pressure drop in the system isn't as great as perhaps we thought when we spec'd it. One of the techniques was to take this balance feature of it and balance it down, back the pump down on its curve so that it doesn't overload the motor, because it's capable of pumping more, that the system is allowing the pump to really swing way out on its curve, is the expression, and it's moving too many GPM, wasting energy, and it could potentially cause cavitation and overload that motor. So over the years, the practice was to take this balancing feature and back it down to slow down the pump, to back it up on its curve. But at the same time, if you think about it, that's also kind of wasting a little bit of energy. And so as the ASHRAE and the hydronics industry looks at that, they might come up with a different approach and say, look, let's put the proper size pump, maybe trim that impeller to more appropriately fit the needs of the system instead of consuming more energy than we need, and then just eat up some of that energy right here with that balancing valve. Real quickly, on the suction side, suctions, this isn't a flow control valve, but I just want to point that out. A suction diffuser, it's been around a long time, relatively speaking. It was developed by Gil Carlson. He was one of had his hands on it as far as an inventor. And this is its purpose. Prior to the development of that suction diffuser, this is what the hydraulics industry, Hydraulics Institute and the hydronics industry had to do. When you use one of these base mounted pumps, you had to provide a minimum of at least 5 times the pipe diameter. So the length of X was at 5 times the pipe diameter that you were using to attach that pump. And the reason is this: if you took that elbow and you brought it right up close to the entrance to that impeller, when that water is traveling through that impeller, it's at different velocities on one side versus the other. And it kind of unevenly would load the impeller, and behind the impeller is your bearing assembly and your seals, and you could damage it very quickly. So they quickly realized, okay, let's give it this straight run of pipe to even out that uneven velocity that's occurring so that when it entered the pump, it was evenly loaded. When this device was invented, what happened is you can see inside here, we have these, what they refer to as straightening vanes. And they take the place of that 5 pipe diameters, water entering into the suction here. This straightening vanes evenly loads that water so that when it attaches to that, it hits that impeller, the impeller itself is evenly loaded. I guess we'll talk real quickly. We'll get into this flow control valves real quick. The gentleman sent me an article, sent me a picture. He was having a problem, and he had a 2-story home, 2 zones, first floor, second floor, flow control valve, and then 2 circulators, first floor, second floor. Family does the basement over. They created a family room. The plumber comes in, puts in a third zone in the basement, and puts the pump on it right here, adds to the manifold, taps off of this T here to feed the basement zone. Ever since he did that, there were times when the second floor just could not heat properly. It wouldn't get warm. And so he's out there and he's trying to figure it out. So he makes this drawing and sends it to me, and we talk about it. And as we spend some time, this is another purpose of flow control valves. In addition to preventing that gravity flow, they also act as a check for reverse flow. And here's what I mean. When the second floor zone was calling and the basement zone was off, this is what would take place. Remember, high pressure here on the discharge wants to get back to the suction of that pump. When he hits that T, he has 2 options. He can go through the boiler and pick up some BTUs, pass through the flow control valve up to the second floor to get back to the suction of that pump. But he also has this option. Because the plumber or the heating contractor was kind of being cute and didn't provide a 3rd flow control valve, he saved himself a couple of bucks. He created an open circuit. The water would move backwards. So he didn't pick up any BTUs from the boiler. A little bit did go through the boiler. They mixed, but water wasn't warm enough. It was too cold. Now, what made this challenging is if someone was to happen to turn the thermostat on in the basement zone and this pump comes on, it completely changed the pressure differential here. Now this pump did go through the boiler, picked up the BTUs, and heated the space. So it was kind of an intermittent problem. But more importantly, what I just want to share with you guys today, and ladies, is just the flow control valves prevent gravity circulation. They prevent reverse flow as well. How many are needed for each zone? Typically, we're going to use 1, but every now and then you come across that crazy application where you might need 2. And this is kind of shown from a primary-secondary manual of a secondary circuit, whatever this is, baseboard, terminal units, radiation, whatever, secondary pump. They're showing flow control valves on the supply and the return. And the reason for that was this. On this example here, I have hot water constantly moving across this crossover bridge into the return. It's another whole subject we talked about earlier this week, but primary, secondary. And what they found was this hot water constantly going across that set of T's. They didn't have an issue here because of the flow control valve, but they had this open circuit and you could get heat migrating. It wasn't a pumped flow, but just heat would go to cold. And so to prevent it, they added that flow control valve, or another option was build this underslung thermal drop, this thermal leg. So in some examples you come across, it's not every day. Most days today, we're going to have copper piping or even PEX tubing, so the diameter and all of that, the volume of water in that system is much less. You usually get away with a flow control valve on the supply and you're fine. But every now and then, the moon and the stars align, and we have this situation where it's set up and we get some reverse flow, not reverse flow, but some migration, thermal migration. And the quickest way to solve it is just to throw that second flow control valve on the return. So a next component that we want to bump up against this morning is air separators. Very important. And first, here are some examples of some commercial, residential, micro bubbles or micro scrubber bubble removers. And this we'll get into each technique and how it does what it does. First question though, where does the air come from? If I got a system completely filled with water, how could air get in? And it actually comes from within, H2O, right? Um, Oxygen is part of water. And there's a couple of things you want to be aware of. Water can hold air in solution, and it's based on the temperature and pressure of the water. The hotter the water and the lower the pressure, the more air will come out of solution. So you have a hydronic system, you filled it, you're starting it for the first time. You've got a lot of, you filled it with street temperature water. There's a lot of air in solution. Now, as you heat that water, air's coming out. What they're trying to show here with this quick example of a glass of water is, if you could do your own little example. You went over to the tap, took a glass, filled it with water, put it on the counter, walked away, and came back, X number of minutes later, you'd start to see these air bubbles kind of gathering along the sides of the glass. Where are they coming from? They're coming from because we lowered the pressure and the water's starting to warm up to only room temperature. Imagine it being 180, 190 degree water, tremendous amount of air comes out of solution. So we got to catch that air. We don't want the air to get out to the system because it'll be nothing but a nuisance. Noise, air binding, reduced heat transfer, can cavitate circulators. So air, we want to address air right in the mechanical room, right where it's released and before it gets into the pumps and gets out to the system. Years and years ago, like 100 years ago, gravity hot water, this is how they handled it. Obviously, the flow rate was very, very low, but they would have this open style expansion tank that was used both to make sure that the system was completely filled with water, because that was the highest point up in the attic, but also would have an overflow. And any kind of air bubbles that were released would slowly find their way up into this tank and vented out through the vent and overflow. Today, or over the years, I should say, this is referred to when you see steel compression tanks. Anytime you see a steel compression tank, that system is known as air control. And the concept was to control the air, not get rid of it, but control it and direct it, constantly direct it up to the steel compression tank. It was a whole system. They had a special fittings. They had an air separator here to catch it, and they would direct it up. This little fitting here actually had a dip tube that stuck down about 6-8 inches into the boiler. And so when that circulator came on and he was looking to provide heat out to the system, the water in the boiler had to go down into that dip tube and out to the system. And because this boiler is such a wide spot in the river, the velocity is very low in here. Any air that was released was allowed to gather at that collar and be directed up to that tank. Today, and for the last X number of years, expansion tanks, diaphragm expansion tanks have taken over. This whole system is referred to as air elimination. Any of the air that gets released when I'm heating in the water comes up this riser, passes through some type of air separator. There are different types, but the point of it is whatever I release, get rid of it. Air eliminate. Air elimination is a system because I don't need that to control it. I already have a source of air in this tank, and it's separated from the system by this beautiful diaphragm that's inside the tank. So air separators or air scoops, this is a pretty common residential, very inexpensive. The industry doesn't use too many of them anymore. They kind of go to a little more effective technology. But just real quickly, this is how it worked. Generally speaking, it's kind of viewed as a commodity. But to be honest with you, there was a little bit of engineering that went into that. And all it was based on velocity. I have 1.25 inch air scoop. So this is the diameter right here. The engineers would make sure that air scoop's diameter here internally would be such that when the water was moving at 4 to 5 feet per second, that's the standard, and you would have learned that through that system sizer class we took last week. As soon as that water enters into this air separator and it's going 4 to 5 feet per second, it immediately would be reduced to 1/2 foot, 6 inches per second, wide spot in the river. Air was allowed to separate, and it would move out of this vent right here, this opening right here, to either an old style tank or more commonly today to a float vent. That was the key to it. What happened was over the years, as boilers got smaller, and the manufacturers of these scoops, Thrush, B&G, Takeo, etc., they always said, look, For this to be effective, we need about 18 inches to 24 inches, a straight run of pipe after this elbow before we enter into this air scoop, this air eliminator. And the reason for that is this: when that water gets heated and it releases some air bubbles and the circulator's on, the water and air are rising up this riser and it encounters this elbow. And this elbow causes turbulence. And when I have turbulence, some of that air rides along the bottom of the pipe. By giving me the straight run of pipe of 18, 20, 24 inches, Mother Nature takes over and the air is now riding at the top. And it allows this guy to do his job. What happened was, over the years, the installer said, this looks awful aesthetically. This is hanging so far out past this boiler. So they started moving that air separator closer to that elbow to make it look aesthetically pleasing. And in doing so, it made sure that the air would get, a lot of it would get right past that air separator and get out into the field. So hence comes along these micro bubble scrubbers. And they're referred to as coalescing mediums. They have these stainless steel little fingers, and they're designed to catch small bubbles, medium-sized bubbles, big bubbles, didn't matter. They just did a good job. And the concept had nothing to do with really slowing down velocity, straight run of pipe. You could actually put them right on the top of the boiler and act as an elbow. But the point was, you use this micro bubble, this scrubber, to catch these air bubbles. You gave it surface tension. And when enough smaller bubbles got together to become a big bubble, then they would exit out and enter, exit out, be eliminated through the air vent, the float vent on the top. Air separators. This guy here, a low loss header, a primary secondary. It can act as an air separator. We talked about this in primary secondary, but it's also an air eliminator. Because the way it's designed, the velocity inside here, similar. Whatever diameter pipe we have attached here, the engineers, when they manufacture, they make sure this diameter here allows the water to drop down from 4 to 5 feet per second to less than a half a foot per second. So the slow, quiet area, air bubbles are allowed to gather at the top here out through the high capacity vent. As you move into a commercial application, this is kind of very, very popular. It's called a rolled air trough, and it's an air separator. and it's tangential connections right here. So I'm coming in here to get out of here. What happens is I'm forced to, what I'm experiencing is this centrifugal force again. And the air and the water are spinning, and the air is lighter, and it's allowed to gather on this collector tube. Get a picture of it here. So as the water is spinning, chasing after the suction of that pump, it through centrifugal force is spinning to the tangential outlet to the pump suction. The lighter air bubbles are allowed to gather and vent out. Typically, it's going through a high capacity commercial vent. So that's how roll air trolls. It's a centrifugal air separator. So it's a different principle. So that's how you treat, but you have to treat air somehow in a hydronic system. And you kind of go from the very simple to the more expensive, more effective, depending upon your application. Another component that's very popular, very necessary, so that a hydronic system, maintains its integrity for years and years and years, is some form of expansion tank, compression tank, diaphragm, steel. Why do you need a tank? Well, when you heat water, the water molecules kind of get all excited and they expand. And so the volume of water increases. I have to have a place to put it because water, like we mentioned earlier, isn't compressible. If I didn't have that expansion tank, or I had a tank that failed, the way we would know that is we would have a relief valve that hopefully it's doing its job. And if it is doing its job properly, it will relieve that pressure to protect the boiler and the system from exploding. If you somehow didn't have that relief valve, you could have a bomb on your hands. So it acts like a spring to maintain a minimum pressure in the system, especially at the high points, and it absorbs the volume increase without allowing the relief valve to open. So these are just some sizing charts, but it's a known fact that the volume increase takes place as the temperature increases. We don't dig into that. Couple different compression tanks. They're all referred to as compression tanks, but over the years, expansion tank became kind of the common term. but they're compressing. You're compressing a gas, you're compressing the air. Old style, water and air see each other. Modern style, diaphragm with a butyl diaphragm between the water and the air. And then a bladder style where you have a tank filled with air, and then this bladder starts to fill with water as the system starts to heat up and the water expands. And again, the water and air are separated. So you have the ASME, non-ASME, commercial versus residential, bladder or diaphragm. We use them in hydronic systems. We use them in potable water. We use them in well water. There's all kinds of applications. Potable water became popular when the codes changed and we had to start putting in either check valves or more commonly backflow preventers on our cold water line that's coming into the house off of the city main, because at night, overnight, when say we took showers and then we heated the water and there was no more use, and that heated water expanded, pressure would start to build. And as that pressure built, it would just back its way back onto the city main. Well, they eventually made a decision saying, hey, we don't want that water. Once it's in your house, we don't want it back in the street. And so they installed these backflow preventers, these check valves. And all of a sudden, they were getting complaints of relief valves popping on these water heaters. And as it turned out, they needed to start adding these potable expansion tanks to accept that expanded water. So it plays a couple of important roles, if you will. Maintains a pressure within the acceptable band, meaning what's it take to fill it, and then what's it take to, or what's my relief valve? So I want to make sure I don't activate my relief valve, because every time you do activate the relief valve unnecessarily, you're dumping water, system water, onto the floor, which that in itself is a nuisance. But when the system cools down, the pressure reducing valve is going to sense a drop in pressure and it's going to replenish. And now you're bringing in cold water that has what? More oxygen that's going to eventually damage the system. The oxygen will attack the cast iron. Provides adequate NPSH. This is not the day for NPSH conversations, but it's very important, especially as you transition to a commercial application. You definitely do not want to damage those high capacity commercial pumps, and NPSH is out of that subject. And like we said, absorbs thermal expansion, may act as a receiver for separated air. That's that old style compression tank. And like we talked about, serves as the pressure reference, the point of no pressure change. Wherever that body of gas is located, the pump in your system wants to reference that point. We always want to pump away from that expansion tank. So a picture of an old style coming off of some type of commercial air separator. I don't want to vent the air. I want to direct it up to that tank and replace that air. So I never want to have automatic vents in one of these old style. Whenever you walk into a basement and you see a steel compression tank, if it's still active, make sure there are no automatic vents, because an automatic vent does a very good job of releasing air. I don't want to release the air. I want to catch it and control it. They actually had some fairly, looks like just like a simple little cast iron fitting sitting there, but they actually had a job on how to have this system, ensure that that air control system works. So they had an air troll fitting that worked with the steel compression tank. And it was very important to have that so that you could establish the proper water to air level when you first commission that heating system. Very important. I show this picture just real quickly because I get a kick out of it. Here we have a couple of high efficiency lock-and valve boilers that were specified by an engineer and then installed by a contractor, according to spec. But the engineer specified a new ASME compression tank that he has installed with an old style inline air separator with a properly sized line to that fancy, what actually on the inside is fancy, on the outside just like a piece of cast iron, air troll fitting. So the engineer, here he is kind of combining probably what he was taught when he was a younger engineer with the air troll, and then he's accepting or embracing the modulated condensing boilers, kind of a contrast, if you will. Pre-charge tanks. Pre-charge means filling the tank with the compressed air before connecting it to the systems. the tank must be pre-charged. This is important. It's a simple little sentence, but it makes or breaks the success of that tank working properly. The tank must be pre-charged to the cold fill pressure. Whatever that fill pressure is, that's what the pre-charge is. Most tanks come shipped 12 PSI, but that's not the magic number all the time. And another thing, when they're shipping, the DOT, Department of Transportation, doesn't want these pre-charged tanks pre-charged any more than 12 to 15 PSI, especially crossing state lines. So anyways, expansion tanks, they come pre-charged. What's happening here, this is a great little picture. When they're pre-charged, there is no water in them. When you attach it to a system that hasn't started the boiler, so the water's ambient temperature, I really don't want any water in that tank because that's how this tank is sized. He's only sized to see the accepted water in as the system water gets heated, it will enter into this tank and it will compress that air and the pressure will rise. But when the tanks are sized properly, that increase in pressure is below the relief valve. We keep that system water from discharging onto the floor. This is the same thing as this, just shown in a commercial application. I have a roll air separator. I'm eliminating the air. I have my diaphragm tank, noted PNPC, point of no pressure change before the suction of that pump. This is a properly installed system. How are they sized? How do we size an expansion tank? Over the years, what's happened is the industry kind of thinks it's based on BTUs over here. They'll come out with these charts, all the manufacturers, Amtro, B&G, etc. They provided these sizing charts, and they start with a column on the far left-hand side saying BTUs. But as you look at it, you kind of quickly say, well, wait a minute. I have a 150,000 BTU boiler. What tank do I buy? Well, right in this chart, you can see that actually I could use 3 different size models for the same 150,000 BTU boiler. So you quickly start to realize that water volume plays a huge part, and BTUs has virtually no part in how do you size a tank. You also notice at the very bottom on these sizing charts, there's a couple of caveats. Based on a 12-pound fill and based on a 30-pound relief in the water temperature no hotter than 200. Any of those criteria change, maybe a 3-story building instead of a 2-story, or a different relief valve, and this chart becomes useless. And this is the formula. This is how expansion tanks are sized, which is another reason why they made these charts. No one's going to sit down and do this, or not too many people, but that's how it's sized. So it's based on volume of the system. So that's what this top part here is. How much water do I have? What's the temperature change? And then what's the pressure change? Meaning fill pressure and relief valve pressure. I have to make sure that I have a volume of a tank that can accept the change in volume, change in temperature, which will affect the volume, at a certain fill pressure, and keep it below the operating pressure of that relief valve. So that's why these charts were developed over the years, to make it easy for the industry. But it has to meet, you gotta support the initial fill pressure and then make sure you stay below the relief valve. So it has to be big enough to accept that expanding water. Volume of the system, the operating temperature, and then the fill and the maximum pressure in the tank. It's kind of a good picture. As it's warming up, there's a thermal expansion of that system water. It's starting to creep into this tank, squeezing that air. And at design temperatures, I have full acceptance of that expanded system water into the tank. So another component I just want to touch real quick. We're up against PRVs, or pressure reducing valves, and that's their role is to fill the system and make sure it's filled to the proper fill pressure. And how are they set? Most of them come out of the box set for 12 PSI. Why? Because the majority of the applications are only installed in a 2-story building. And when you do the math, in feet of height from the boiler to the second floor piece of radiation, when you do the math, it's typically about 8 PSI. And the reason it's 12 is we want to have positive pressure at the high point. So kind of a rule of thumb was always, whatever it takes to get to that high point, that's what we're trying to show over here, divide the number of feet from the basement, the fill valve, to the highest point by 2.31. Whatever that number is, add 4 PSI. So now I know, regardless of the height of the building, whatever that height is, I have positive pressure in that radiation, fan coil, baseboard, cast iron radiator, whatever it is. So in feet of height, divide by 2.31. What that's doing is converting it to PSI, because downstairs here at the boiler, I'm reading the gauge in PSI. So I want to see what it is, PSI, add 4 to it, you'll have positive pressure at the high point. That's a good practice for fill valves. Where's the best place to locate a fill valve? Ideally, you want it in the line that is the point of no pressure change, so that that valve diaphragm is truly sensing what's going on in that system. You see it right here next to the air trough, which is very close to that expansion tank connection. And you see it right over here where the expansion tank's connected and the fill valve's right there at the top. We don't want anything else like pump operation or anything that could turn on or turn off and suddenly affect the diaphragm of that valve, and suddenly he responds unnecessarily. One last thing to touch on, relief valves, very, very important. They have engineered, according to ASME, boiler and pressure codes. They're one of the most important things that we hope never activate, but they have to be there. So they have 2 ratings, or 2 measuring points. One is the pressure. So whatever that heat exchanger or that boiler's maximum pressure, I have to be able to relieve that. I have to unload it at that certain pressure, so my diaphragm is calibrated to that. But the other part is, I have to, when I do relieve, I got to make sure that I can meet or exceed the boiler's heating capacity. If I can open up at the right pressure, but that boiler can develop more energy than I can get through my relief valve, that thing's still going to continue to develop pressure, and I'm in trouble. So relief valves are based on the maximum pressure and the maximum output of that heat exchanger or that boiler. And that's when you look at a catalog and you'll see a capacity chart, you'll see it. It's based on relief valve pressure over here on the left-hand side, and then what are my BTUs? Monolimit capacity in BTUs per hour. So you got to meet those. Very important how they're installed. If you have an existing relief valve in a mechanical room and it's leaking, obviously this is a definite don't do this, but someone, and took a picture of it and sent it to me, installed a second relief valve, which is definitely a no-no. Another picture that was sent to me was, hey, my relief valve's dumping on the floor. It's driving me crazy cleaning it up. Well, why don't I just dump it in my condensate pump and take care of it that way? Again, another no-no. There are very specific guidelines from the relief valve manufacturers on how to install them. Like on boilers, they want a outlet, elbow, another pipe all the way down, probably no more than 2 to 3 inches from the floor. The reason being, if it did relieve for whatever reason, people are around there, we don't want them splashed. You don't want to get damaged by it. So anyways, that is the end of the presentation here. I realize I've gone over a little bit more than I wanted to, and I apologize for that, but I appreciate everybody attending and staying with it as long as we could. I see that there were some questions. Rob, I don't know if you were able to answer some of them, or is there still some remaining questions we want to address?
George, we got a bunch of them answered. However, we just got one here from Steve. I haven't gotten a chance to get back to him, but if you can touch on him. Really talks about a 30-pound relief valve coming with a boiler.
Yes.
And then really how high can we run that expansion tanks and fill pressure before we run into that problem with that 30-pound relief valve?
It's a function of the how tall is the highest piece of radiation above the boiler room, because that's going to establish that fill pressure. And the higher that building is, the higher the fill pressure, the closer we're getting to that 30-pound relief valve. We see this all the time in downtown Boston. A brownstone contractor puts in a residential boiler from a local supply house, comes with a 30-pound valve. Has a 5-story building. He has probably 24, 25 pounds of fill pressure right off the bat when the system's cold. If you were trying to operate in that manner, you'd need an expansion tank probably bigger than the boiler room to accept that water and still keep that pressure from only climbing 3 or 4 pounds versus, the relief valve blowing. I can't tell you how many times we've walked into these mechanical rooms and there's a garden hose attached to the bottom of the pipe of the relief valve, and the garden hoses run from the mechanical room out into the courtyard. And it's done by the super of the building because he's sick and tired of picking up the water that's splashing onto the floor, because every time the boiler goes to its high limit, the initial pressure is so high and the expansion tank is so undersized that the pressure builds, the relief valve blows. So in an example like that, you'd have to, kind of either call us, do some calculations, but when you getting into those taller buildings, you need a higher setting on your relief valve so that you don't have that issue of the 30 pound. But at the end of the day, to answer the question, whatever the fill pressure is, if I have a 30 pound, I'm going to plug in those numbers. I want to know the volume of water and I want to know the temperature change. And once I plug that in, either in a computer nowadays, years ago, it would have been that math formula that I showed you, that's going to say, hey, this is a size tank you need that will accept the heated system water and still keep the relief valve from blowing. But you'll be amazed at how big that tank's going to be to stop the relief valve from blowing. I don't know if that answers that, Rob.
I think that does, George, and I'll certainly follow up with Steve once we're offline. I'm sure everybody's got somewhere exciting to go on a Friday afternoon or Friday morning during quarantine.
Well, it probably feels like Friday afternoon because I spoke too long.
That wasn't bad at all, George. It was put in there. And then as questions came in on the chat, George, what we've done is we've put some of the related information in the Dropbox folder that's going to get emailed out as a follow-up here. So
awesome. Thank you.
Give them some stuff. All right.
That's great. Yes. If there are no further questions, I just want to say thank you. I really appreciate everybody, spending, some time with FIA and whatever, sharing information back and forth. Like I say it every time, but we're going through a crazy time right now, and we pray for everyone, or hope for everyone to be safe and be smart about this. But if we can share some time together and share some information, just kind of general system information, we'd love to do it, and we'll continue to do it until such time that, we get the green light and we can maybe get back to whatever that new normal is going to be. And I don't know what it's going to be, but we'll all figure it out together. But again, I just want to say thank you. We're probably going to come up with some new subject matter, so keep an eye out for it. We'll probably do an email blast as well as post it on our website, just to kind of keep this thing going. So anyways, we appreciate it. Have a great weekend. Thank you very much for your attention. And like Rob was saying, if you have other subject matters that you guys are interested in, absolutely send us an email, put it on the chat, and we'll do the best we can to, satisfy those requests. So I guess without further ado, I think we're just going to end the meeting at this point. And I just want to say thank you and have a great weekend.
Thanks, George.
Thank you, everybody. Thank you. Thanks, Rob.